Hey everybody, I'm Augustus Odina, and today I'm going to talk about joint work that I've done with Charles Sutton on property signatures, which are a way to represent computer programs so that we can do machine learning on their representations. Before I explain what property signatures are, I'll describe a problem that they can help to solve. The problem is to synthesize computer programs like the one on the right, given user-defined input-output examples. This is called programming by example, and it's a well-studied problem. The program on the right is a real program generated by our synthesizer that takes a list of integers and returns the sublist of all elements in the input list that are distinct from the previous value in the list. You don't have to think too hard about the details of this example program. It's just meant to be illustrative of the type of program that you can synthesize using our approach. Let's talk more about how the specification works. A PBE, or programming by example, specification consists of pairs of inputs and outputs. The goal is to synthesize a program taking the given inputs to the given outputs. The pairs given on this slide would all be satisfied with a function taking in an input list and concatenating that list to its own reverse. So, for example, a function that takes true, false to true, false, false, true. Now, we'd like to take this specification and feed it into a machine learning model that we hope will spit out the correct program. But how do we do this? If the inputs are small numbers or strings, then it's easy, but it's not easy in general. For instance, how do you represent unbounded data types, or polymorphic functions, or recursive inputs? All of which this example has. What if we could abstract away all these problems? So, we can, which is what this is about. Say you're synthesizing a program from lists to lists. If you know that the length of the input is the same as the length of the output, that tells you a lot of information about what should be in the program, right? So we're going to kind of lean into this intuition and represent a program with a bunch of other smaller programs. And these smaller programs are going to be called properties. Given a function that takes a term of type in to a term of type out, we can write other functions called properties that take a pair of an in and an out and return a Boolean. Let's do an example. So remember the function from a few slides ago, concatenating a list to its reverse. Here are three properties that could operate on that function, or on any function taking a list to a list. The first property checks that all the elements of the input list are in the output list. The second checks whether the output list has any duplicates. The third checks if the input list has the same length as the output list. If we have multiple input-output pairs, then we need to aggregate the results of a property across the pairs. If the property is always true on the pairs that we're looking at, we say that it has the value all true. And if the property is always false on the pairs we're looking at, we say that it has the value all false. If sometimes it's true and sometimes it's false, we say that it has the value mixed. The list of these aggregated results, which has as many elements as there are properties, is called the property signature. For the concat with reverse example, the signature will be all true, mixed, and mixed if the empty list is one of the inputs, and it'll be all true, and all false otherwise. So what do we gain from doing this? A property signature is a general purpose vector representation of program semantics that we can feed to machine learning algorithms. Since we don't need to use the underlying function to compute the signature, we can do an important trick. Given input-output pairs, we can compute a guess of the signature directly from those pairs. Now, we have a vector representing the semantics of the program we're searching for, once we've done that, and we can feed it into a machine learning algorithm. So one way to take advantage of this trick is to use it to do premise selection. Basically, I'm going to give the system some input-output pairs, and it's going to do some machine learning on those input-output pairs and select premises or functions to be used for the synthesizer, right? Our synthesizer works by searching over all possible programs given a library of functions, and we're choosing which functions go in the library. So the way that we do this is we generate a bunch of random programs to use as training data. Then we generate a bunch of random properties that can operate on those programs. Given both of those, we can compute the property signatures for all the programs, so that we have a big data matrix with as many rows as there are programs and as many columns as there are properties. Then I can train a model to predict which functions were called in the random programs, and this model can produce an output given just the input-output examples, since it can turn those examples into a signature. This works pretty well, like measured in terms of extra benchmark programs it lets us synthesize on a held out test set of programs generated the same way the training set was generated. But this is what you'd expect, right? The interesting thing is that it also works well on a test set of about 150 human written programs. And you might ask, why doesn't this change in distribution hurt us, right? We claim that it's because properties generalize better than other types of representations. For instance, a property comparing the lengths of the input and output lists is invariant to the content of those lists. Overall, we get a pretty good speed up from using machine learning for this. We solve about twice as many of the human-generated programs in about a tenth of the time compared to a baseline. For more information about this, please read the paper. It's on arXiv. We have another paper coming out that uses property signatures that I'm also pretty excited about. So please read that when it comes out as well.